Today we'll be talking about data visualization. Now, data visualization has the potential to allow us or enable us to make better decisions. It takes data that may be in tabular format, that patterns may not be evident upon first inspection. However, if we are able to make good decisions about visualizing that data, those patterns will come to the surface and they'll enable us to see patterns or trends that ordinarily we wouldn't be able to see. This will lead to a much more effective decision making, and it has the power to impact students' lives or whatever population you're working with, whatever stakeholders you're working with, to be able to impact them in much more positive ways. In this presentation, you will learn how to design graphics that will enable you to see patterns in data, and secondly, that will allow you to communicate the data. You will not learn specific programs to create graphics, such as R or MATLAB, or how to use Excel. That topic is too immense to cover in a short period of time, such as this. Let's start by taking a graphics quiz, just to see where we're at with our knowledge of graphing. First question is, what is the best way to display percentages or parts of a whole? Second question, what are all the problems with this graphic you see here? What things do you struggle with? What things would you rather see different about this graph? Question number 3, what's the difference between charts, tables, graphs, and diagrams? This is somewhat contested in the field of visualization, and I have a specific way that I will be describing these, but in your mind, what's the difference between charts, tables, graphs, and diagrams? Question 4. Looking at this three-dimensional graphic, what is the problem or problems that you see with this graphic? Question 5. What is the reason or reasons for displaying data in a graph? Question 6. Looking at this plot, what is a major flaw in this graph? What could be done to make this graph more accessible to more people? And our final question, what are the two major goals to accomplish in designing an effective graph? We'll revisit these questions, this quiz, later at the end of the presentation to see what you've learned. Let's begin by talking about why it's important to effectively learn to graph. Stephen Few puts it this way, visual representations not only make the patterns, trends, and exceptions in numbers visible and understandable, they also extend the capacity of memory, making available in front of our eyes what we couldn't otherwise hold all at once in our minds. In simple terms, information visualization helps us to think. That really means better decisions. If we're able to more effectively communicate and more effectively find patterns in our graph, we'll understand what the data is telling us, and this leads to better decisions. Another important factor to remember is that 70% of our sense receptors are located in the eye. We have a powerful pipeline coming into the eye, and we should be able to take advantage of that pipeline. Let's look at it with an actual example to show you what I mean by how powerful visualization can be. Here we have a graphic or a data that's represented in tabular format, and this more plays to our auditory or our verbal memory. I'd like you to look at this table and try to figure out what the data is telling us, what narrative or what story is it speaking to us. What patterns or trends do you see in this table? If you're like most people, there's really 8 numeric values in this data and some demographic labels. It's not a whole lot of information, but it's too much information to hold all at once in working memory. If we go ahead and turn this verbal output into something that's graphic, as we see here, we can now start seeing that, a trend does come to light. We see that for all populations of students, it doesn't matter if it's gen ed, special ed, charter school, public school, we see an increase in engagement from males to females. The one exception is in general education students in public schools. We see females have a decreased engagement level. This is interesting, and it's really not visible or available upon first inspection if we're looking at just the table format. However, when we see it visually, this pattern comes to light very easily. There's a problem though with visualization. Starting early, or around 1620s or the early 1600s, visualization really was given birth. And you see from this trend line that the graphing quality, that's on the y-axis, has increased slowly over time. And then around at this point here, at the end, toward the end, we see all of a sudden a decrease. If you were to make up a narrative for why we see this decrease in graphing quality, what event happened in that time period? With your knowledge of history, what do you think happened in this time period that caused this decrease in graph quality? Stephen Few puts it this way: having means to create graphs with a computer doesn't guarantee that we'll do it effectively, any more than having word processing software makes us great writers. Take a look at this Few quote. It's related to the previous slide. And go ahead and read that. If you're like most people, as you're reading through this quote, you may start to judge me as the writer for the choices I've made with colors and text and fonts and such. Or if I were to use grammar that was poor, or if I were to use spelling that was incorrect, you may judge me. Yet we don't judge people when they use poor quality visualizations. We see these poor visualizations all the time in academia. We see them in popular media. People are constantly using poor quality graphics, yet they're not called into question as if though they would be if they had used poor quality language skills. Let's actually read this quote in a more easily readable fashion. Few puts it this way: people sometimes do this, that is, use poor graphic choices, because they've seen similar charts in newspapers or on the web, and they are naively following a bad example. People who knew better sometimes do this because they care more about the visual impact, that's the eye candy, than the clarity of the communication. If we wanted to tell the truth in a way people can easily understand, this is not an effective approach. It's similar to the harmonica. I play the harmonica and I don't play it well. But the harmonica is a nice little instrument because you can just start blowing it. It doesn't matter who you are, you can play the harmonica. It's in key. You just start exhaling air and it sounds like you kind of know what you're doing. And it's easy to play. And visualization is similar. In the 1980s, what happened was the advent of computers, and that's what we saw in the previous graph with the trend. In the 1980s, with the advent of the personal computer, anybody could make graphics easily. And this was good and bad. People started making graphics easily, however, they didn't have the training to understand behind creating graphics, and they've made poor ones. Similar to, I can easily play the harmonica, but to truly master the harmonica like the masters do requires understanding music, understanding the instrument I'm playing, and that takes time and dedication. Just merely knowing Excel or some program and being able to spit out a chart doesn't mean you'll be able to use graphics effectively. Let's start now by beginning to build a common language. I'll use this language throughout the rest of the presentation. People use graphs primarily for two reasons. The primary reason is to gather information from data that they can't otherwise gather. That is, they're looking for patterns and trends that aren't really available upon inspection of the data in a tabular format. Secondly, they're looking to be able to convey that information to other people. That is, they want to become more effective communicators through graphics. Let's discuss charts, graphs, tables, and diagrams. This is somewhat contested in the field, but few defines charts, graphs, tables, and diagrams this way. Charts is the umbrella term, and under that falls tables, graphs, and diagrams. Tables are just numeric values that are placed in rows and columns. Graphs would be the visual representation of those tables, and then diagrams is usually some sort of visual representation of a process. Two other terms that I'll be using: quantitative and categorical. Quantitative, you may or may not be familiar with, but it means numeric representation. Some sort of variable that's numeric. So that could be absentee, or test scores, or frequency counts. And categorical is more demographic type variables. That could be age, sex, race, socioeconomic status, special education, things of this nature. And we'll also be talking about geomes. Now, geomes, I think it's easiest really to see an example of what geomes are, but geomes are the geometric shapes that we use to represent quantitative data. That's the primary way we represent data. Let's look at the four major ones. There are more than this, but these are four major ones: bars, boxes, lines, and points. And I've shown two different types of lines and two different types of point representation, but these are the four major geomes that are used to represent quantitative data. Let's look at the parts of a data, or the parts of a graph. Often you'll hear in elementary school or secondary education that there are specific components of a graph, such as title, axis, scale, and this is somewhat true but not fully true. These four components are really three components. They should be, are true of all graphs. You have a primary data component, or primary data design. In the graphic here at the right, those would be the dots. These are your geomes. So it's your bars, your points, your lines, and your boxes, or whatever geome you're dealing with. Then you have secondary data component design. These really play a supporting role. So your primary data component should pop. That should be the thing that stands out above all the other data design components. So this secondary data design, that's your text, grid lines, scales, legends, and things like that, title. They play a supporting role. They really should not be in the forefront. They shouldn't be overshadowing or overpowering the primary data components. Tufte puts it this way: above all else, show the data. And that's what you want to do. Show the primary data component first, and the secondary data component design, that plays a supporting role. Then you have the non-data component design. That's your background, and generally you don't think about that. You would if we had a black background here, though, as you would probably want much lighter writing in axes and such. And then the fourth component, which you really shouldn't see, is chart junk. In this visual at the right, we see beaker. That's chart junk. It doesn't play any role in supporting or showing the data. It may catch your eye, but it distracts from the data. If you have something in your graphic that distracts from the data, you should get rid of it. Let's dig a little deeper now that we've built that common vocabulary. There are certain rules of perception, and if we can harness those rules and understand those rules, we'll become more effective at finding patterns in our data and more effective at communicating those patterns to others. Let's look at one of those rules. Here we see sets of circles. We have A set and B set. If you look at them, one set is convex and one set is concave. Give you time to kind of look those over. And if we take those same exact circles and rotate them 180 degrees, now all of a sudden the opposite set has become convex and the opposite set has become concave. This is because of a rule that's hardwired into our brains. Our minds perceive light as coming from above. This is perhaps because of the sun. In any event, circles with the lightest area at the top indicate that they're bulging out, and the dark area is at the bottom. This makes sense geometrically. Whereas if a circle is light at the bottom, we would understand it to be concave, because this makes sense geometrically with light shining from above. This is hardwired into our brain. There are other rules like this, and if we can understand those rules, we'll become more effective at finding patterns in our data and also to be able to communicate those patterns to other people. Let's understand a little bit more about how the eye-brain system works. It's one of many systems in our body that help us with perception. We have, for instance, Ware puts it this way: there are separate memory subsystems for processing auditory and visual information, as well as subsystems for bodily movements and verbal output. This is one system that we'll be looking at in detail. They're all kind of connected to one another. They all take part in the brain, but they need those appendices, such as the eye or the skin. And in this particular eye-brain system, we're looking at the eye-to-brain relationship. And what happens is the image hits the eye, goes to the retina, where it's transformed into electrochemical signals, and then this is sent to the brain, where it's then processed. Let's dig a little deeper into this. We're going to use an imperfect metaphor to understand this. Our brain works much more complicated than what I'm about to explain here, but it's useful, this metaphor, for the talk we're having here today. The computer system we'll use as a metaphor for our brain, particularly a computer system that's hooked up to the internet with modern computers that we have today. Computers consist of three different parts. Generally, you have some sort of buffering system, some sort of working memory, RAM, or and then also some sort of hard drive. Now, the buffer we all experience if you're trying to download a YouTube video or something like that, and it says it's buffering. And what's happening is information is being sent to the computer, and it hasn't gone into the working memory yet, and it needs to get buffered first before it's sent to the working memory. Then the working memory is where we actually do our computations or whatever on the computer. That's when we have the different applications or programs open. If you've opened up too many programs and you get some sort of crash, you've overworked your working memory. A similar thing can happen in our minds. And then we have the hard drive. That's where we store information that we want to keep long term. That's when we save it to the hard drive. In the brain, we have a similar type systems. Similar to the buffering in a computer is the iconic memory. And we'll talk more about these parts of the memory, of the brain memory, in a moment. Visual memory, that is. We also have a working memory for visual, and then we have long-term memory. The iconic memory is temporary. It's less than a second. And we don't actually keep everything that we see. So for instance, if you've driven to work or you drive somewhere, chances are you rarely remember almost none of that trip. What you saw, the places you passed, chances are you don't remember much of it. That's because it was taken into the eye and it went into the iconic memory, and most of what you see is discarded. The iconic memory deems it this is not important to keep or to work with. And most of what enters into your visual conscious in the iconic memory is discarded. You don't even really think about it. Realize that this is preattentive. This is almost animalistic in a way. You're not really conscious or thinking about what's happening in this iconic memory. And we'll talk more about what preattentive means. And at this point, you have a decision process going on, and it's passing to the working memory things that are important, that the iconic memory deems important, and things that it doesn't deem important are simply discarded. The working memory is also limited. It can only hold 3 to 4 chunks. If you try to put more than that in there, you will need to discard some of the chunks that are already in there. It's also temporary. It only lasts for about 3 seconds to a few hours if you rehearse whatever you're working on in your working memory. Your long-term memory is really the goal with data visualization, but it's not the focus. If your graphics are geared towards the iconic memory and working with the preattentive attributes in the iconic memory processes, and also you are working on the limitations of the working memory, making sure you're not overloading the working memory, which only holds 3 to 4 chunks or bits, then you'll naturally reach the goal of putting that information in the long-term memory. And that's really the goal of visualization. The actual overarching major goals, though, of data visualization isn't necessarily to put it in the long-term memory. We want that. But what we really want as we're making our visualizations, and what we need to be thinking about as we're making them to help achieve the getting that information into the long-term memory and be able to make important decisions with that, we need to think about those preattentive visual attributes that grab and direct our reader's attention. That happens in the iconic memory. And then also we need to think about how to work within the limits of the working memory. If we focus on those two things, the preattentive attributes, and working within the working memory's limits, we're more likely to be able to grab our reader's attention and to be able to communicate effectively and to see patterns and trends in our data, and we'll be able to make better decisions. Here's an example of what preattentive attributes are. I've used that word. Here we see a string of numbers, and I'm going to ask you to count up the fives, all the digit fives in that string of numbers. There are 9. Probably took you some time because these all look the same. However, if I add the preattentive attribute to the fives, a preattentive attribute of color to those fives, it now becomes much easier because the iconic memory has a much easier time of grabbing the information that's important. You can easily count 1, 2, 3, 4, 5, 6, 7, 8, and 9 fives. This is an example of the use of preattentive attributes to help display or convey our message more easily. There are other preattentive attributes of a visual perception. Here are some that Few has described. 3 that are of particular importance are length, that's from the form, 2-dimensional position, and then also color, the hue. The 2 that are particularly important for quantitative or displaying quantitative information, values such as test scores or frequency counts, are length and 2-dimensional position. 2-dimensional position works really well for quantitative information and not so much for categorical information. So don't waste this very important preattentive attribute and use it wisely, but this is a very effective means for displaying quantitative information. Length is as well. And you'll notice that many geomes, such as points and bars, are made up of these preattentive attributes of length and 2D position. Now for displaying categorical information, hue, colors, the hue is very important. It grabs your attention quickly. Shape also works for this as well, but probably the most prevalent one would be color or hue, or more powerful, I should say, not prevalent. Let's take a look at an example of a preattentive attribute. Now they're great for grabbing readers' attention in the iconic memory, but keep in mind they're not like Jello. There's not always room for more. Here we see 2 gray boxes with sets of shapes, and we're looking for a red circle. And we can easily find it. It's in the second right-hand box. And it's easily found because we only have one set of preattentive attributes. That would be color. And as I said, this is the best one for displaying categorical information. Let's go ahead and look at another comparison. Here we have two gray boxes again, and it's again pretty easy to find that red circle. Not as easily as it was when color was the preattentive attribute. In this case, what is the preattentive attribute? If you said it's shape, you're correct. And here we have the circle is the only difference. And you're able to still find it pretty quickly. Shape is a pretty decent means of displaying categorical information. Not as effective, though, as color. And now when we start displaying two preattentive attributes, both shape and color, finding that red circle is more difficult. Think of it like this. Few puts it this way. If you were to look up in the sky and you see a sky full of seagulls and there's a hawk there, it's easy to spot the hawk. But if you see a sky full of different varying birds, it's not as easy to find that single hawk. And sometimes these are some examples of times where people overuse the preattentive attributes. Maybe they use too many colors, or they use too many colors and shapes, and it just overloads the usage of preattentive attributes. And if you highlight everything, nothing is meaningful. So highlight what's important. Well, let's look at some do's and don'ts for achieving visualization's two goals. Remember, those two goals were to use preattentive attributes effectively and powerfully, and then also to reduce processing demands on the working memory. Don't do 3D. And reason one for why we shouldn't use 3D, we see an MC Etcher drawing here, and it's very difficult, and in fact impossible, to figure out where the highest point is in these stairs. And the reason is humans are not very good at distinguishing three-dimensional space. Very good at the two-dimensional space. Remember, two-dimensional position was the best way to display quantitative data. However, three-dimensional space were much more poor at distinguishing. Also, with three-dimensional figures, we'll see that often bars or lines or whatever, the geomes are obscured, as they are in this example. And some software developers will say, oh, well, we have interactive software that allows us to turn our software, and then you can see those obscured bars. And this is true, but this is also very poor because it's overloading the working memory. You get this perspective here, and then you've got to twist it, and you're now putting a lot of stuff in the working memory, and now you've lost what you had before, and it's very difficult to keep it all in your working memory at once. Also, if you look at these two bar graphs that show the same information, the one on the left may look slightly prettier, may or may not to you, with the 3D bars, but it's more difficult to tell what the data is telling us because it's distracting from the data. It's just extra stuff that Tufte calls chart junk that's really not necessary, and it takes away from the data. A better approach to the third dimension is to use faceting. This allows us to keep everything in our working memory at once and to see all the data at once. Allows for easier comparisons too, because we're looking at lengths, which is a powerful preattentive attribute. Now, faceting is easy in some programs such as R. That graphic there was used or created using ggplot2 in the R program. You could also do the same thing if you take Excel and create individual graphs of each of the variables. That is the red bars here in the three-dimensional diagram, the blue bars, and in the red bars. You can create three different graphs and just merge them together in Excel. So you create them in Excel and merge them together in maybe something like Microsoft Word. And there's other programs that do faceting as well. Second thing we should do is, if we can use horizontal, that is with bars or with dots, plots, if we can use horizontal, go ahead and do that if it makes sense. The eye is able to distinguish differences in vertical length, but it's easier for us to distinguish differences in horizontal length or position. An exception to this is if your x-axis is time. Do not switch it to the y-axis. This is because historically time is on the x-axis or the bottom axis, and if you switch it to the y-axis, this could cause confusion. This is just because of the historical reasons behind it. Also, if you can order your bars or order your dots or put order to the plot, go ahead and do that. We have on the left the horizontal bars, and they're listed alphabetically. If we go ahead and we order them by count size, we start to see patterns and trends much more easily. It's more easy for us to start making patterns and trends across our data. Don't use pie graphs for percentages or parts of wholes. Rarely are pie graphs a better choice. Sometimes they may be with glyphs on a map and in other certain circumstances, but generally there are much better ways to display percentages or parts of a whole. And if we look at these two pie graphs, we have a two-dimensional. A three-dimensional is even worse, as we've already described why the problems three-dimensional attributes have with them. But the problem is, let's take a look at the UK and US here in this pie graph, and I ask which country's GDP is larger, and it's very difficult to tell, and that's because we can sense geometric area as a preattentive attribute, but it's much more difficult, and there are better preattentive attributes that we can use than this preattentive attribute. Let's go ahead and look at an example of a better way of displaying this. Here we have a dot plot, Cleveland dot plot, that displays the same information. In here, it's much more easy to tell the difference between the UK and the US. And we can see that, oh, the UK does have a larger percentage-wise GPD or GDP. Also, I want to make note that all the data in this presentation is made-up data, so please don't think that any of the data is actual real data. And also, if you can eliminate a legend, go ahead and do that if it's reasonable. The reason is, on this graphic here on the left, we have a legend. Both of them were made in ggplot2. But the problem is, when you're looking at the plot and then you're looking at the legend, you're looking back and forth, that's putting extra strain onto the visual working memory. And remember, we can only hold 3 to 4 chunks in there at a time. So if we can reduce those processing demands and put the labels right on the graphic, it makes it much easier for us, our eyes, and our brain-eye visualization system to sort out the information and keep it all in the working memory at once. Don't use red and green together. The reason is 10% of the male population and 1% of the female population is colorblind. And if you use reds and greens together, this sector of the population sees just dull browns for everything. A better way to approach this could be to use a palette that is much more reasonable. Color Brewer, you can Google that. Color Brewer gives you some choices for color palettes that are more friendly for colorblind individuals. And a better approach altogether may be to facet. Here I have faceted the same information, and all of a sudden some trends appear that are much more difficult otherwise, and we're able to use just black and white ink. And here, particularly with the girls, we see there's a trend for all the girls to go from pre to post down, with the exception of one individual. That's interesting, and that might not be as visible when we have all those lines together, whereas the faceting gives us the ability to pull out that pattern. Don't use pattern fills. That's hatching or whatever you want to call it, to fill bars. Sometimes we feel that we need to because we're trying to represent some other third variable within a bar graph. But there's better approaches. We can use color gradients, or you could use faceting, or you could use direct labels and eliminate the legend altogether. And the reason we don't do that, let's pull this up. Here we see an optical illusion where things start to move on us and it's hard on our eyes. This takes advantage of the same pattern fills that I often see people use in their graphics. And people do use this for a reason. They're using it because they're not allowed to use colors, probably. And so they're getting around that with pattern fills. But it's a very poor choice as it wreaks havoc on the visual system. And just keep in mind that as you're creating your graphics, you want to maximize pre-attentive attributes, the impact of them. Don't overuse them. Highlight the data that's important. As Tufte says, above all else, show the data. Use the pre-attentive attributes to really show that data. And then reduce processing demands on the working memory. It only holds 3 to 4 bits or chunks at a time, so reduce processing demands whenever you can. Let's take that quiz now that we took at the beginning and discuss those answers. What's the best way to display parts of a whole percentages? And the answer to that is there is no best way. A dot plot is a reasonable choice, but a pie chart should be avoided in most cases. Question 2, what are the problems with this graph? And if you look at it, the primary data that we talked about, those would be the geom, the dot, the points, really kind of fall into the background with the coloring, the gray. And then we have this thick solid box around it, and the grid is dark, it's black, it's dark, and we have colored labels and very large font, and the secondary data really is standing out. We should really minimize this and play a supporting role of the primary data. Also, more specifically, there's no title. The grid lines are overwhelming. The axis scale numbers are overwhelming, and the axis labels are overwhelming and in red and distracting. The box around the graph is too thick. To see an improved version of this, look at it. Here's an improved version where the data now is highlighted as the main component. Question 3, what's the difference between charts, tables, graphs, and diagrams? According to few, charts are the umbrella term, and tables are raw numeric values arranged in columns and rows. Graphs are the visual representation of information found in tables, and diagrams are the visual representation of a model or a process. What's the problem in question 4? What's the problem with this graph, this 3D graphic? And in this graphic we have the problem of occlusion, where bars are hidden behind other bars. It's very difficult with three-dimensional figures to determine which bar is longer or which dot is closer. It's much more difficult with the third dimension added, because we're not so good as human beings at determining three-dimensional pre-attentive attribute. Question 5, what is the reason for displaying data in a graph? And the answer really is it's to encode more information into less bits. In other words, data representation visually allows more information to be analyzed in the working memory. This leads to better decisions. Question 6, what's the major flaw in this graph? And this is the use of reds and greens that show up as brown to colorblind individuals. A better choice would be to use faceted graph, or to choose a better palette. Question 7, what are the two major goals to accomplish in designing an effective graphic? And you really want to focus on the pre-attentive visual attributes that grab and direct our reader's attention, and how to work within the limits of working memory. If you focus on those two things, the pre-attentive attributes and maximizing them, and then secondly on limiting the processing demands on the working memory, you'll be much more effective in your data visualization. This brings to a conclusion the presentation on data visualization. If you'd like more information on data visualization, Stephen Few has two excellent books that are fairly inexpensive, A about data visualization. I'll highlight those two as excellent sources of information. Tufte also has a number of good books on data visualization, and Colin Ware also has an excellent book on data visualization that you can find.